Before we have an announcement, so Dima proposed to speak, and he proposes to speak not maybe tomorrow but Thursday in the afternoon. So everybody is okay. I remind you that if someone wants to speak, should think carefully about it and then suggest. Not carefully. Sorry about that. Okay, so far we had only one proposition by Dima, so I don't think you are shy, right? So don't hesitate. Think carefully. Think carefully. Okay, so the talk is today by Claus, and he suggested that since the talk is about two different topics, he suggested that he's going to speak about half an hour for the first topic, and then we make a break. Since we have the room until 12 if we want. Normally the talks are about 1 hour, but then there is also time for discussion after that. So Klaus will speak first topic approximately half an hour, then we'll make a coffee break of 15 minutes, say, and then come back for the second part of the talk.
Okay. Good. Thanks very much. So it's my great pleasure, of course, to be here in Cambridge and to have been asked to give a talk here. Thanks very much to all four organizers, in particular the two ones that are here, Jean-Bernard and Marcus. And as Jean was indicating, my talk is on two really quite different topics. So the first part addresses a question that was asked by Herrn Sturmfels several years ago. The background for this question is that in polynomial optimization, as we all know, positivity certificates by means of sums of squares identity are omnipresent or are sort of at the bottom of the entire theory. Now, even if my initial data, like a polynomial that we want to show to be non-negative, even if it has exact coefficients like rational coefficients, all the algorithms usually perform with floating point numbers by their very nature. So if the certificates that they might eventually produce will by nature be inexact. They are floating point numbers, and it can even happen that they produce an apparent certificate for non-negativity, and in fact the object in question is not non-negative at all. So errors may occur due to rounding errors in the floating point. So it's an interesting question to understand, at least in principle, to what extent can we expect to have exact certificates, for example, in terms of rational numbers if our initial data was using rational numbers. So it is this context in which the question was asked. Namely, we are given a polynomial, multivariate polynomial with rational coefficients, and we assume it's a sum of squares of polynomials with real coefficients. Does it follow that it has a sum of squares expression with rational coefficients? And the answer is no. And this first part of my talk, I want to tell why, give an example, and discuss a little bit the background. So actually the example is right here. It's about it's probably the easiest or one of the easiest examples. You see it's a homogeneous. I homogenized it, which is not important, but for the discussion it's more convenient later. It's homogeneous in 3 variables. Where's my pointer? x0, x1, x2 of degree 4. And in fact, it's a sum of 2 squares over the reals, but not a sum of squares altogether over the rationals. And this is not an isolated example. I just put it here for explicitness, but there is an entire series, or there's entire families of examples that we construct. And so this is in 3 homogeneous variables. So for any number of at least 3 homogeneous variables, for any even degree at least 4, we can construct sort of large families of examples. So before I go into this example and the discussion, let me first recall what kind of positive results on behalf of Sturmfels' question were known before. So by just general reasons, it is easy to see that when you have a rational polynomial that is SOS over R, then you find a sum of squares representation not just over the reals, but over some finite field extension of the rationals, some finite real field extension. And now, depending on what we know about this finite extension K of Q, Sturmfels' question may actually have a positive answer. So depending on the nature of K, we may actually be able to conclude that we can descend the SOS representation to the rationals. And this is a result that was proved by Chris Hiller in 2009, and a little bit later, Ronan Carrés gave a different proof and also improved on the bound that Hiller gave. So this statement is, suppose we have this polynomial with rational coefficients, which is a sum of squares over a totally real number field. Totally real means, so K is a finite field extension of the rationals, for example, given by the minimal polynomial of some primitive element. And totally real means that all its places are real. Or if you give K by a primitive element and its minimal polynomial, then that means this minimal polynomial will have all roots real, only real roots. So if this is the case, then we can actually conclude F is sum of squares over the rationals. And even more, we can give a bound on the number of squares we need over the rationals in terms of the number of squares we need over this K on the one hand, I call it M, and in terms of the field degree K over Q. So this is by definition is the dimension of K. It's a Q vector space. And roughly the answer is that the number of squares I need over the bigger field, over this K, gets multiplied by this field degree. The actual bound is a little bit more, but the order of magnitude is roughly the product. So Chris Hiller gave a bound which was much worse or much bigger, and Ronan Carrés arrived at this bound here.
So is this K over which F is always in SOS? Is this always can you always choose a successive quadratic field extension?
No, because if you could, then you could really descend. Because, for example, for a real quadratic extension, you can. I mean, if you make a quadratic extension, it depends whether you kill order rings or not, or whether you kill real places, or whether you create non-real places or not. But okay, no, I understand your question. No, it's certainly not iterated quadratic usually. And on the other hand, I'm not sure if it's iterated quadratic. Probably the answer to your question is again negative. So K might be iterated quadratic extension, but there's other examples that can be totally real. Yeah, I mean, just take any irreducible polynomial over the rational numbers with only real roots. Take the adjoin the 0 or take the corresponding field extension. So this will be totally real.
And your counter example, if you do it with map, there is a package doing symbolic computation, right?
Yes.
Did you try it?
No.
I'm curious to see
I used symbolic computation for the example I did in the beginning in the first slide. I will discuss it later again. Actually, the situation is really very nice because the proofs are completely explicit and constructive. So once you are given an SOS representation of f over k, you can really explicitly write down a corresponding longer SOS representation over the rationals.
Is this sharp?
It's pretty sharp. Renaud Carré gave a series of, I mean, it does not, his examples don't cover all cases, but I think for, I don't remember, for what kind of, maybe it's only for quadratic extension, which is of course quite restricted, but it seems to be sharp, yeah, pretty sharp. And yeah, one can still extend this result from sums of squares to weighted sums of squares. So this last formulation gives such an not a generalization. So suppose f is again our rational polynomial in question, and suppose we have fixed weights, other polynomials with rational coefficients h1 to hr, and we are interested in writing f as a weighted sum of squares. So we want to write it as a sum si hi, where the weights si are sums of squares. Suppose we can do this with sums of squares si over k, then we can descend the thing. So we find other sums of squares si over q with the same identity. So in other words, or briefly, the results generalizes for this kind of field extension.
So
Yeah.
what is the assumption for f? So you saw f is the sum of squares over the reals.
Yes.
So in this theorem is
Over the reals, that's sort of the starting point. But I immediately know if I have it over
conclusion is
the
the f is just over the rationals. So what is the assumption here?
assumption is
The
assumption is f is SOS over k.
Oh, okay.
That's the
So
assumption.
not over the reals.
Well, then it's of course also over the reals. But no, I mean when
Now
it's
you confuse
we start with assuming it's SOS over the reals. Then we know by general theory. I mean, we find an SOS expression over some finite extension, finite subfield of the reals. I call it k. Now this k can be nice in the sense that it's totally real. Then we can apply all this. Or it can be not of this nice type. Then I don't know anything right now. Right. So I assume from the outset f is SOS over this k. K satisfies these conditions. Then we can.
So you know the field for your counterexample on the previous
Yes.
slide?
Yes. Later slide. So here, here for your convenience is the initial example again, and I'd like to discuss why it is a sum of squares over the reals on the one hand, and not a sum of squares over rationals on the other. So the first is in fact shown by this slide here, because, yeah, I don't know if you want to check this now. Take beta, an algebraic number satisfying this relation. So it's an algebraic number of degree 3. So this equation has 3 real roots, these ones, 2 negative, 1 positive. And if you, for any such beta, this identity is true. So I've written f up to factor 1/4, which I put on the left-hand side in order to have nicer expressions. So f is 1 square over q beta minus beta times another square over q beta. So this is not exactly a sum of 2 squares, but you see, if I join still a square root of minus beta, and if I take one of the negative values for beta, then I can adjoin the square root of minus beta and still stay real. And then over this larger field, q adjoint square root minus beta, I have written f as a sum of 2 squares. I mean, that's not how the thing was proved, or also, the thing was constructed and proved by, of course, in a different way. I'm doing reverse engineering now. I provide the result, but don't tell how I arrived at it. But this shows, I mean, there's actually two representations of f as a sum of 2 squares over the reals, namely by using these 2 values of beta. gives two different, it's easy to see that they are different, two different SOS representations of the reals as sum of two squares. And it's, or as a side remark, we can note that for this particular f, we can in fact write down all SOS representations over the reals, because, so as we have just seen, there are two as sum of two squares, and every other one is a convex combination of these two up to a natural notion of equivalence. So if I, what people call the Gram spectraedron of a sum of squares is this set of the convex compact set of Gram of positive semi-definite Gram matrices or Gram tensors. And in this case, this Gram spectraedron of F is an interval, compact interval with two endpoints. The two endpoints correspond to the two ways of writing F as a sum of two squares, and all the points in between are the convex combinations. So they are sums of four squares, not three. Sums of four squares. So this is the situation over the reals. Now, why is it not SOS over the rationals? And this depends on the fact that F is in fact a sum, it's a product of four linear forms with complex coefficients. And the coefficients of these linear forms, I don't write them down. I mean, I could, but it's kind of, yeah. The coefficients are, again, algebraic numbers, and these four factors are mutually Galois conjugate to each other. So we can start with L1. It's a linear form, A times x0 plus B times x1 plus C times x2. ABC algebraic numbers, and then I perform Galois automorphisms sort of the algebraic closure of Q, and then I get for example A prime x0 plus B prime x1 plus C prime x2 and so on. I get four different ones, and these four I'm multiplying up, and this gives F. So this is just a fact in this case. And now the geometry of the situation comes into play. I wanted to, from time to time, to make a little drawing at the blackboard. So we have homogeneous polynomials in three homogeneous variables. So this corresponds to the projective plane, and it's useful here, or it's preferable to use projective setting rather than affine setting, so to be homogeneous. So in the complex, so this is just a symbolic drawing, not the real world, but the complex world. I have these four lines. Now I need a line that intersects all three. I have already drawn. For example, like this. These are four lines, L1, L2, L3, L4. So we see, at least if the lines are in general position, like here, so no three go through the same point, we have altogether 6 points of intersection, which I may label Pij is the intersection of the line I with the line j. So these are points in the complex projective plane. And out of these 6, so for example, this is P12, L1 cap L2, this is P23, and so on. Out of these 6, 2 are real and 4 are not. So for example, let's say this one is real, P12 and P34, which would be this one. Let's say these 2 are real, and the other 4 come in 2 pairs of complex conjugate points. For example, like these 2 may be conjugate and these 2 may be conjugate. In fact, the situation is like this, that the real points arise if L2 is the complex conjugate of L1. So coefficient-wise, L2, so these are linear forms. I would have to fix a complex embedding to start with, but then I can coefficient-wise conjugate them, and so if I intersect a line with its complex conjugate, I get a real point.
Then the conjugation is not this.
Maybe it's not this. I didn't think about it. Let's remove the. It's probably wrong. Yeah. but the other two come in I just drew as in a random way. And again, L3 is, or L4 is conjugate of L3, so this is how the real points arise. Now comes the important point. So this is not true in general, but it holds in this example that these 6 points Pij are all Galois conjugate among each other. And this has to do with a Galois group that is acting behind the scene here, being sufficiently big, sufficiently transitive. So all 6 are Galois conjugate over Q. So over the rationals you cannot distinguish them. And rational polynomials won't distinguish them. So one rational polynomial that vanishes in one of them automatically vanishes in all of them. Now you see what happens. I mean, suppose we have an SOS identity for f over the rationals as a sum of forms G nu, so that would be quadratic forms since f is degree 4, G nu with quadratic forms with rational coefficients. We have 2 real zeros of this PSDF, namely these 2 points P12 and P34. And of course, in such an SOS decomposition, all the summands would need to vanish in these real zeros of f. So that G nu have rational coefficients vanish in P12, for example, that's already sufficient. And by this Galois conjugateness here, they vanish in all 6 of them. So all the G nu would have to vanish in all 6 points. But this is not possible for quadratic form. It's too many conditions. So usually, I mean, you may remember from geometry classes, you have heard 5 points in the plane determine a conic, but 6 points is usually a.
Why there is no conjugate?
Yeah, why?
Why the last statement?
Yeah, because through any 5 points you can find a conic, parabola, hyperbola, so over the complex numbers. So 6, if you add a 6th condition, it doesn't work anymore in general. And it's just, I mean, this is not hard to prove. I could.
And also, you have 3 points on the line, which would
Yeah, that's the point. Yeah. Right. You have a quadratic form that suppose it vanishes in all 6 of them. So for example, let's look at this line. It vanishes in these 3 points, but it's quadratic, so it has to vanish identically on this line. And this holds for all lines, so it just doesn't work.
So this is a recipe to build up other example, right?
Yeah.
That's what you mean by.
Yeah. Yeah. Exactly. Yeah. So what I did to construct this example that we are discussing here, this particular f, what I did was to start with a linear form L1 with coefficients in some degree 4 extension of the rationals. Well chosen in the sense that its Galois group, or the Galois group of the Galois hull is large. It's a symmetric group on 4 letters in this case. And then takes the Galois conjugates, multiplies them up, and this will, I mean, whenever I start with such data, this linear form has to be sufficiently general, so because I have to take care that the 6 lines, for example, don't look like, I don't know, something like this. The 4 lines shouldn't be like this. They should be in general
not
position.
in one orbit. I mean, this orbit is the orbit of L1 under the Galois group is bigger.
No, it's
No,
these 4.
So it's
These 4.
so it's sufficiently general.
So
but
my Galois group is
this
so I have a degree
orbit is
4
short.
extension. My Galois group is a transitive subgroup of symmetric group on 4 letters. But what I need for I mean, it's if you like a little Galois theory, it's easy to explain. What I need for this conjugateness of these 6 is, I mean, they correspond to pairs of those. So I need kind of 2 transitivity, and so the Galois group has to be either full S4 or the alternating group in this case. And then I multiplied them up. I mean, here I used some symbolic, but Maple can do it. I mean, so I didn't do it by hand. And this way I arrived at the initial example. Okay, so let's see, there's some questions arising. I kind of sketched the general procedure to build such examples. So instead of degree 4, I can use any even degree, at least 4, instead of 3 of working in the plane. I can work in any dimension, at least 2. I have to be a little bit more careful with the arguing, but there's no essential difference. And so one can show, this is just remarked here, that if you look at forms in 3 homogeneous variables of degree 4, ternary quartics, so there's a theorem by Hilbert that any non-negative ternary quartic is over the real the sum of squares, in fact of 3 squares. We have just seen a ternary quartic with rational coefficients, which is of course the sum of squares over the reals by Hilbert, or by what we have shown explicitly, but it's not SOS over Q. So for this class ternary quartics, one can show that this construction produces all counterexamples to Sturmfels' question. But for more variables or higher degree, I'm convinced that there's many more counterexamples. So, I mean, what would be interesting to discuss is, for example, this set of questions. Because you see, what we used in the argument was in a very important way, we were using the real zeros. I mean, we have some f over q, which has a few real zeros. And now in any SOS representation of this polynomial over q, all the summands need to vanish in those. So if we can arrange things like these real zeros have a much larger Galois orbit, and we cannot find any form of the required half degree that vanishes in all these points in the Galois orbit, then I have a counterexample. So we use the real zeros. Are there also examples without real zeros, without projective real zeros? So this, I don't know. Or another sort of question. I mean, coming back to the beginning, I started remarking that suppose we are given a finite extension of the rationals, have our polynomial over the rationals, and we assume f is SOS over k. Say k is real. So under what conditions can we conclude that f is SOS over q? So we have seen in the beginning, if k is totally real, we can make this conclusion. But are there other conditions on k over q that would allow the same conclusion? In particular, I'm wondering if it's maybe true if the extension is just of odd degree. I know of no example where k over q would be odd, so it has a real place automatically, and this conclusion would fail. And this last question here can be more generally asked for linear matrix inequalities, solutions of linear matrix inequalities. And I checked that if you have a linear matrix inequality in one variable, I mean, this is very, very, very modest. So I have something like, I have one variable x, and I have symmetric matrices A and B. And this is my LMA, so x is just one variable. And A and B have rational coefficients. And suppose there is a real, this has a solution over some odd degree extension of the rationals. But we have to be careful what we mean by solution. Solution should mean the resulting matrix is non-negative under all real places, not just under one. Otherwise it cannot work. So does it follow that there is a rational number? And this is true in one variable, because I mean the geometry is so easy, you are on a line. And the real solution set is either an interval with non-empty interiors, then you are done anyway, because it contains a rational point, or it's an isolated point. And in this case, you have to discuss that. Yeah, maybe one more slide on this first topic, and then we can make a break. So, wondering what kind of exact certificates you can get for non-negativity of a polynomial f, like the one we discussed over the rationals. So we see, although it's the sum of squares over the reals, it's not necessarily 1 over the rationals. But what one can always do, and this was suggested by Marie-Françoise, who is here, is to look at representations with denominator, in the sense, or in the same spirit as Hilbert 17. So any polynomial with rational coefficients that is non-negative is a sum of squares of rational functions over the rationals, so of fractions of polynomials with rational coefficients. Or in other words, that's equivalent. There is a sum of squares over the rationals, a polynomial sum of squares, that f is a quotient of a sum of squares by this one. So we may look at the examples that we have constructed here and ask what is the minimal degree of such a denominator over the rationals. And so here's a result. If we have a degree 4 polynomial, like the one we showed, there is always such a denominator of degree 2. And in fact, the situation is very nice, because we have a completely explicit construction for all these possible denominators. It's explicit. Also, for example, we know the product, the numerator is the sum of 5 squares, either 5 or 3. This depends on a number field that's behind the game.
And it's independent of n.
Independent of the number of variables.
Usually, if you don't assume q, you would get 4 squares, right?
It's 5 because it's easy to say, because what matters is you need shortest possible expression sum of squares equals 0, with not all in the number field that is behind the scene, with not all summands 0. And so it means you write -1 as the sum of r minus 1 squares. And now this is probably widely known that in a non-real number field, -1 is sum of either 1 or 2 or at most 4 squares. So in the worst case we have 4 here, so we can do here with 5. In the case we have discussed at the blackboard, the number field has level 2, so we get along with 3 here. So here's, just for fun, here's a possible denominator. So h is this quadratic form. It's a sum of 3 squares of linear forms. And I mean, this is elementary. This is just a matrix, diagonalizing this matrix. And these 3 forms of degree 3, so f times h has degree 6, sum of 3 cubic forms. Stepping back once, when the degree is larger than 4, then this only, I mean, the argument only gives a lower bound for the possible degrees of denominators. So the same argument shows that we need at least denominator of degree 2 less than the f.
But that doesn't mean that you know that there is one of this degree, right?
There is
It's
one.
at least.
No, there is.
So you think you guarantee that?
There is certainly one h, but
Yeah,
we need at least this degree.
At least
I mean, by Hilbert or by Artin rather.
But the question is the degree. How much? Which degree can you
I
guarantee?
don't know.
that?
I have no idea.
Huh?
So I would think that probably this is probably the correct degree. But I mean, you see, if degree of f is 4, we are in an easy situation because h has degree 2 then. And a quadratic form, to check that a quadratic form is a sum of squares, you just need to check that it's PSD, that it's non-negative. Whereas so here, I mean, I find certainly an H of this degree such that the, what do I want to say? Such that FH is SOS and H is PSD, but I don't know that also H is PSD. So, but probably this is the correct one. However, please bear in mind that this statement is only true for the class of counterexamples that follows this particular construction in this talk here. So this is not about all counterexamples, but rather this particular series of examples. So we could make a break now and then.
Is there a way in algebra to measure how exceptional this counterexample are? And dimension.
Well,
I don't know how to express that.
I mean, in the sense of
I don't know.
of course, it's a zero set, but this is not a good answer. I mean, it's a usual form would be, for example, ternary quartic would just be smooth. Have no singularities, and I mean, this is not only not smooth, but it's a union of 4 lines. I mean, which is
So
for a degree 4 curve to be a union of 4 lines is extremely rare, of course.
So for a ternary quartics, you have a complete
Yes,
classification,
yes,
right? So
yes.
that's the
Exactly,
only case.
exactly. That's the only case. Yeah.
It's counterintuitive.
Yeah, but this case is best understood by Hilbert already.
I
and-
mean,
and
you wouldn't. I think if you show it to many people, they would say that any deformation of this curve would give you an example still. But
yeah, but deformation is.
so minus
I mean, this is
before-
an arithmetic question, and deformation doesn't
so
preserve the
deformations are
arithmetics.
really non-arithmetic.
Hmm.
What do you think about matrix values? How do you see the extension?
Haven't
You
thought
say
about it at all.
2 by 2. We want to factor 2 by 2
Hmm.
polynomial.
Hmm. Yeah, but I mean, the answer can only be negative, I think.
So
I would-
sure you
I would expect. I
cannot
mean, if
do
you-
it over Q.
No. I mean, what if I mean, if F is my example from the talk, if you want 2 by 2 matrices, if I take this matrix, I mean, could it be sum of, if F is not SOS over Q, could this be sum of squares of matrices over Q? No.
No,
You have
I mean-
consolation curve.
No. Diagonal entries become sums of squares when you have a matrix.
Diagonal.
Yes.
Okay.
Because they are times the same.
No, but I'm asking the complexity, the
Yeah.
degree extension.
Hmm. No, I haven't thought of it.
Anyway.
Okay, thank you very much. The second talk.
Okay. Thanks for returning. Yeah. So, second part is concerned with the so-called Helton-Knee conjecture, but in fact, this question was discussed before Helton and Knee made it a conjecture. For example, by Nemirovsky in a plenary talk on the ICM in Madrid, 2006. And so this problem concerns linear projections of spectrohedra, alias SDP sets, semi-definite program sets that are suitable for semi-definite programming. So let me briefly recall the setup. We call a subset of Rn projected spectrohedron, or just an SBP set. If it is a linear projection of a spectrohedron. So if you forget for the moment the exists Y in Rn and just read the rest, well, if you take this inequality, it defines the spectrohedron in the x, y space. And so by this quantor here, by this existence quantor, this means it's a linear projection of a spectrohedron. So such sets are very suitable for doing semi-definite optimization on them, because if you have a linear objective function that you would want to optimize over such a set, you can as well lift it back to the spectrohedron that you projected, and so the problem becomes a semi-definite program, and as such it is considered to be easy. I put it in quotations here because we yesterday heard that semi-definite programs are not in fact so easy always or altogether. But the question, I mean, it is clear that any projected spectrohedron is on the one hand semi-algebraic, on the other hand is a convex set, but no other necessary condition is visible, is obvious. And so the question was asked by Nemirovsky, is conversely every convex semi-algebraic set such an SDP set? And this was, so Helton and Ni had two large papers in 2009, 2010, where they gave lots of sufficient conditions on K, or on the convex hull of a set to be a projected spectrohedron, and they upgraded this question to a conjecture. So that's why it's nowadays usually referred to as the Helton-Ni conjecture. There's lots of people who have worked on this question and found sufficient conditions, so I listed a few here that came to my mind, but certainly this list is not complete. A general answer is, however, missing, even if the convex set is compact, for example. So to go a little bit into what I want to present here, I have to recall the moment relaxation method, which is, correct me if it's wrong, I think due to Jean Bernard and to Pablo Parillo. What one does is, I'm starting with any subset or any semi-algebraic subset of Rn, S, let's call it S, and we try to get a hold on the convex hull of S. What one does is to consider probability measures on S, and well, for any probability measure on a set, if I take the expectation,
K should be an S.
K should be an S. That's very true. It was a K before. This K is an S. Thank you. So the expectation vector, sort of the average of all the points, lies in the convex hull of S. And now you relax these linear moments. Sort of you relax truncated moment problem. And the setup is a bit technical, but many of you have seen this, but just to agree on notations, let me briefly go through it again. Let's assume more specifically that S is a basic closed set given by finitely many simultaneous polynomial inequalities, H1 to HR. Let's just put H0 for convenience. And I don't want to assume all the way that S has non-empty interior in Rn. So usually I think of it as being some lower dimensional set of which we want to take the convex hull. So we have usually a non-zero vanishing ideal, so the ideal of all polynomials that vanish identically on the set S. Let's call it I. And now we consider weighted sums of squares of these inequalities H sub I, modulo this ideal. And we are fixing some positive integer d and consider such weighted squares with sums of squares Si, but not all sums. We don't allow all sums of squares, but only those for which all the summands have bounded degree at most d. So all these expressions here have total degree at most d. So this is a subset of the space of polynomials of degree d. We can put M the union over all these, and we get what is called the quadratic module generated by these equations and maybe by the ideal. In any way, this MD is a closed convex cone in the space of polynomials of degree at most d. Closed is related to adding here the full vanishing ideal, otherwise would not be guaranteed. And its dual cone, forget the one for a second, MD dual, so the set of all linear forms that are non-negative on MD is a spectroedron by an easy argument. So I can as well intersect this spectroedron with a linear condition, mu of 1 is 1. This is also a spectroedron in the dual space, so prime denotes dual vector space of Rxd. And now what one does is to evaluate these linear forms in the dual case on the tuple of variables x1 to xn, and letting mu run over all these linear forms in the dual. So these are sort of generalized probability measures. They are not probability measures. I mean, anyway, they are only restrictions to degree at most d. But the idea is that these are the conditions to be in MD star is a weakening of being a probability measure on S. And so this is certainly a convex subset of Rn that contains S and therefore also the convex hull of S. And the bigger I make the degree d, the smaller this case of d gets, so the tighter the approximation of the convex hull by these projected spectroedra gets. So we have this hierarchy here. We let d get bigger and bigger, and there are some prominent instances in which this approximation is a good one. I think I'm not sure to whom this theorem should be attributed. I think it's you proved it first, right? Yeah. So forget the dots. We assume S to be compact, and so if M is Archimedean, M was this quadratic module generated by the inequalities here. Archimedean, need not discuss it, it's a technical condition. And if I have a compact set, this Archimedean is easily achieved by maybe adding another inequality. Then the convex hull, the object that we are aiming at, is the intersection of this nested sequence of projected spectrohedra. So this means, since matters are compact, up to an arbitrary epsilon tube around this convex hull of S, I find some k of d inside this. So I can at least approximate the convex hull as closely as I would like by projected spectrohedra. And the situation is even better under an additional condition. So S is still compact, and this is the condition that this M sub d, so the quadratic module with bounded degrees on the summons, contains every linear polynomial that is non-negative on S. So if this is satisfied for some d, then this projected spectroedron kd that we constructed on the slide before is equal to the convex hull. So in this case, conv S is certainly an SDP set. So the terminology is that the relaxation is exact or is becoming exact in this favorable case B. And just to rephrase it again in less technical terms, I say it again, if we are trying to represent the convex hull of basic closed compact set S, and if we want to follow this pattern suggested by Jean Bernard, we should find a system of inequalities for S, describing S, H1, HR. So we can take many if needed, but some finite system, such that we can write every linear polynomial non-negative on S as a weighted sum of squares using these weights but, and this is a crucial condition, with a uniform degree bound on, so uniform in all these linear ones. For a single one, I may be able, but I need it to work with a uniform degree bound on the summands for all these L. And this, if this can be done, then in fact the data is explicit, or the construction is explicit enough, so if we have achieved this, we can write down explicitly an SDP representation of this convex hull. So here's a few recent results. Namely, the first one says, so the results are on convex hulls of one-dimensional sets. They are all only about this case. First result says if you take any semi-algebraic set in some R to the n of dimension 1 and takes the closed convex hull, this is always an SDP set, it always has projected spectrohedron. So in particular, if the set that you started with, the set S is compact, then the closed convex hull is the convex hull, Kara-Theodori. And you see that the convex hull is a projected spectrohedron. And then after discussing with Tim, he suggested ideas to even do more, namely if we are looking at sets in the plane, it can be, so he has techniques, or he has a paper where he studies non-closed sets, writing them as SDP sets, and he, for example, he starts with a closed SDP set, and then he removes certain parts of the boundary, and if things are made in the good way, then the resulting smaller set is again SDP. So these kind of techniques can be used to prove the Hamilton-Lee conjecture in dimension 2.
So in the third one, do you assume the study is closed?
No. No. And the third one, I just have any convex semi-algebraic subset. But of course, I mean, how to prove it? You take the extremal points, or you take the closure first of all, then take the extremal points, or closed extremal points. It will be the convex hull of them, and then you have to discuss. I mean, this is a one-dimensional set, and then you have to massage this a little bit. Or I mean, it's a bit technical, but I think it can be done. But the hardest step is to establish uniform degree bounds on curves. So I want to go a little bit more into detail, so I will definitely not give an outline of the proof. The crucial step is to work on a smooth algebraic curve. So if you like, for simplicity, let's assume we have a smooth plane curve. So we have one equation in two variables x and y, p of xy equals 0, one polynomial. Let's assume this describes a compact, so the real points are compact, smooth plane real curve C. We want degree bounds, so let's just, so I'm simplifying, let's forget an arbitrary closed subset S of the curve. Let's just take S the entire curve. So I'm interested in linear polynomials that are non-negative on the entire curve C. When I say curve, I always mean only the real points. So when algebraic geometers are present, one should have a better language and also not forget the complex points, but here I really only talk of the real curves. But what it comes down to proving these results is more, not just linear polynomials, but polynomials of any degree. And what you need to show is something like what is written here. What you want is to give for polynomials that are non-negative on this compact curve. Let me draw one. For example, may have two ovals. So we consider polynomials of any degree that take non-negative values on C. And first of all, we want to write them as sums of squares modulo the equation of C. This can be done. This has already been known for some time. But we want to write them as sums of squares with uniformly bounded degree. So in other words, So if f is non-negative on C, we want a degree bound on the sum of squares representation modulo. So P is the equation of C. So this just means f is the sum of squares modulo the equation of C. We want a uniform degree bound for the sum of squares. Uniform in the sense that the degrees are bounded by some function only depending on the degree of f. So this needs to be established. And why is this essentially, why is this a crucial step for the results discussed before? Because if you have this for linear polynomials, for dec f equal 1, you would be fine with describing lines that are non-negative on C, like tangential lines, these ones. And so you would describe the convex hull of this. If, for example, you do it for quadratic f here, you are doing the same thing, but not in the plane, but you first perform a quadratic embedding of the curve, a Veronese embedding, by using the quadratic monomials as the new variables. And then you have your curve sitting in 5-dimensional space. And then you are discussing the convex hull of your curve in this 5-dimensional space, and so on. So doing this for all degrees of f means for all as high dimensional as you like embeddings of the curve, you can describe the convex hull of this embedded curve in the high dimensional Rn using Chon's method. So this is in fact true, such degree bounds do exist, but unfortunately the proofs of these theorems are pure existence proofs, so they don't give any clue of the nature of these degree bounds. And for explicit calculations or working with these STPs, of course, you would need to know how far you have to go with the degree. So let's discuss a little bit more the issue of degree bounds, which is the central issue here. Let me start with the affine line, which is essentially the same rational curves that can be parametrized by polynomials or by fractions of polynomials from the rational line. In this case, degree bounds are elementary to find. So I just wrote down one example here. So if you take the affine line, take unit interval, so here's origin, takes the interval -1 to 1, and consider univariate polynomials non-negative on the unit interval. They all can be written as sum of squares plus the sum of squares times 1 minus x squared. So 1 minus x squared is a graph like this, so it's non-negative on this unit interval. It describes this. And so the point is that you have degree bounds on S0 and S1, very easy ones in this case. And this is the reason that it's so easy is that polynomials in one variable can be factored into linear and quadratic ones. Yeah, for example, here, so you use use identities like this. So 1 plus minus x, or let's say 1 plus x, is non-negative on this interval. You can write 1 plus x using here degree 2, and so this is a square, and this is another 1/2 times this one. There's one other case of curves where degree bounds are known, so-called genus 1 curves. So these are curves with an equation of this type. Two variables, so we are in the plane, two variables x and y squared plus some degree 4 monic polynomial q of x with distinct roots to make it smooth, at least 2 roots real, so the curve may look like depending on whether q has 2 or 4 roots, real roots. This is the coordinate axis, may either have 1 oval or 2 ovals. And in this case, there is also this known how explicit degree bounds look like. So to write a PSD polynomial that is PSD on the curve as the sum of squares, modulo equation of the curve, you need to allow larger degrees for the sum of squares, but only up to such a number with a constant n. That so you have to increase the degree of f by some constant that depends only on the curve. So with this varying curve C, this number n may be as large as you like, but still it's always a sort of a linear bound in the degree of n, or even the degree plus some constant. And yes, but that's really everything you know about degree bounds on curves. And so for curves of other type of higher genus, it's just by the theorem mentioned before, it's known that degree bounds do exist, but nobody probably has an idea of how they look like. Getting away from degree bounds, there's another issue. So several people have asked me how the result I mentioned is compatible with the result that people sitting here have proved a few years ago. Namely, they looked at convex sets and tried to, they looked at moment relaxation, Lassere relaxation on convex set. And they have proved that if the convex set has a non-exposed phase, moment relaxation can never be exact. As was what I was saying before was that via moment relaxation, via Lassere relaxation, we can do, for example, every set in the plane. So how is this compatible? And this I would like to discuss here. So let's look at the examples that they discuss in their paper and make the drawing. So this is again the coordinate axis, say take y equals x3, or I wrote it with x1 and x2, so this is the curve x2, x1 cubed. And then they put it something like this. So this is line x1 minus 1. This is plus 1, here we also have plus 1. And they look at this convex set. It's described, I hope, by the inequalities given on the screen. This is K. And here we have a non-exposed extremal point. Because so exposed would mean there would be a supporting line, hyperplane line, that isolates this point on the ZK. But I mean, the supporting lines, so the lines that for which my ZK lies on in one half plane, the only supporting line is the x1 axis here. But it does not isolate the point, it rather gives me the entire interval. So this is a non-exposed extremal point. And by their general theorem in this paper, Lassere relaxation for this ZK cannot be exact. Independent of what inequalities you can use as many, it will never get exact. But I claim that, I mean, my approach is different. I'm trying to write K. I'm trying not to work on K, but rather on some smaller one-dimensional subset of which K is a convex hull. I don't know if this thing is somewhere here. So if there's color chalk, I'm using this set here. Let's take this interval. And let's take this part of the cubic. So if you take the union of those two and take the convex hull, you have the same set. And this violet set is one-dimensional, union of two curved pieces. And so in my approach, I work on the union of these two, and algebraically that would mean, you don't need to read this, would mean more or less what is written here. Right? So I have to work on the curve, which is a union of this line and this cubic. So this has two components. They do intersect somewhere down here. It's not well drawn. So this union of the two curves is not a smooth curve. So I cannot directly apply the results on this union. But what I do is to consider each component separately, sort of take a disjoint union. This is here done, This is here done by taking the direct product of the two rings. Direct product of two polynomial rings corresponds geometrically to the disjoint union of two lines. And these are the parameterization. So you see -1 t parameterizes this line. Maybe is there well, -1 comma t1 parameterizes this line, t2 cube parameterizes this cubic. And so I did it yesterday. I'm not sure if I did everything correct, but in principle, when you do the details correctly, you should end up with an SDP representation of this set, and probably it looks somehow like this. So you can put everything into one big matrix, but it consists of 4 blocks, 1 by 1 block. So this is just this inequality, 2 by 2 blocks, these ones, and 1 3 by 3 blocks. Yeah, and details, as I say, may be wrong since I didn't do it carefully. Yeah, this example does not depend on the new results that I talked about, because the curves here are rational. This is a line and this is a cubic, but which is also a line, or it's rational. So, but I wanted to illustrate this point, how these two, just the statements are different. There's no contradiction. And this example also illustrates another point, namely in, for example, trying to describe the convex hull of some set on a singular curve, because what I proved initially was only on smooth curves. One does not work on the singular curve, but rather one pulls matters back to desingularization, normalization, and thus you reduce to the smooth case. So this technique is used. So last slide. A few thoughts of why doesn't this work in higher dimensions, or why does it only work for convex hulls of one-dimensional sets? So there's two problems. If we try to describe the convex hull of S via Lasserre's relaxation, remember we needed to find inequalities describing S such that every linear function non-negative on S has such a weighted decomposition with sums of squares. There may not just exist any such finitely many H1 to HR if the dimension of S is bigger than 1. And even if they do exist, there may not be any such set for which you have the degree bounds that you would need here. So they may exist, but or for all choices, you may have an explosion of degree bounds. This really happens. On the other hand, I mean, they are. This doesn't say, in my opinion, that this is the complete end of the line. For example, with a singular curve, I also believe that this program does not work directly, but we had a way out by passing to the normalization. So there may be suitable covers of the set living in some, covering it, not in a one-to-one fashion, or even if we need not cover S. I mean, we need to cover anything between S and the convex hull. For example, I mean, this example is done, but just for illustration purposes, let's assume we want to describe this shaded K. So we need, and we want to write it as a convex hull of something, some S. So for the S, we certainly need these two components, but we can, if we please, we can use anything that's inside as an additional component, anything that is between S and the convex hull. And we may cover this in a suitable fashion, and in this way hope to arrive at a better situation. And also, this I haven't mentioned yet, this is one of the real big results in the Helton-Knee papers. They prove that SDP representability is a local property. So if you have finitely many SDP sets, take their union and the convex hull, it's again an SDP set. So if you're working with compact sets, you really can localize as local as you like. You really need only to be able to describe the convex hull of some small neighborhood of any point, and the rest would be done by this beautiful theorem. Yeah, that's all on my side. Thank you very much.
So the techniques to get degree bounds for the strict positive Stellan sets and the degree bound for this, where you have no negativity is allowed. So they are completely different techniques, right? Is it true or not? So the first one depends on the minimum of F, right?
It's different, yeah. For the strict sets, you always have some fancy bounds, which are very bad, right? Very high complexity, but they exist by, I mean,
but it depends on the minimum of F on
yes,
this.
yes.
So I guess this cannot be the same for your the proof of the degree bound, because then you have a zero.
They don't depend on the minimum, because they are supposed to work also when you have zeros.
Yeah, that's
the
right.
whole
So
point.
I'm
Yeah,
saying
exactly.
It has to be different, right?
Yeah, yeah.
Do a function, the degree bounds exist for nilpotents, for ideals rather than reduced curves? Because you say
so.
always you restrict to the curve.
If you look modulo nilpotents, then you are looking finer, in a finer way. So if it doesn't work in the reduced setting, I mean, you only make the question harder.
The degree bounds might be different.
That may be, yeah,
But still.
if you, I mean,
You
what?
have a theorem, which really says that if an OVF, you can reduce.
Yeah, yeah.
You can
Although I think
always
it doesn't work with nilpotents.
Yeah.
I think.
just that the bounds increase.
Yeah, or yeah.
But there was a result by Marshall and me that proved that, for example, if you have the positivity set is fixed in a generator G1, Gm given, then the set of polynomial of certain degree, D, which are non-negative on this, it's a dense in all the polynomial of degree D, which are non-negative on this set.
In what
And
sense?
there will be
in what sense dense?
There would be a polynomial, so still a polynomial equation in the coefficients of the generators, right? And F, so that if this polynomial system of polynomial equation is non-zero, if F doesn't satisfy this equation, then you have a particular positive tensatz, even if it has a zero. So I would guess that maybe
not with bounded degree, not with bounded.
no, but what I'm saying that now, in this feature, it would be nice to check when you can have a bound measuring how far you are from this variety. Probably, you might guess that if you are far away from this variety, then probably you have an easy certificate.
But maybe I understood it wrong, but you say those that you can do with bounded degree are dense?
No. But by using this fact that because you need no negativity, right? You need to accept polynomial which have a zero on the set. But apparently the bad guys are characterized by a system of polynomial equation in the coefficients of the. So maybe now you have a tool to check, well, if you are far away from there, maybe this F has a certain certificate, and if you are very close, probably it's difficult, and if you are far away from this variety, maybe it's easy to get a positive state ansatz. Actually, Nini is talking about that tomorrow. No?
Yeah, I'm talking tomorrow.
Because it's a bit surprising that it's possible to get the bound for the periodic polynomial which are negative on a set. Because the previous technique used a minimum, so in this case.
So you said there in an interpretation of that construction of this on the board in terms of moments, certain measures on this set.
So I should have some way. So this one you have two curves, not one curve. Right? Can you show us how to construct your difference?
Yes.
Yeah, how to get this? Yeah. You almost said you have two curves, not one.
Yeah. How's it done? I mean,
To lift in
so this is
space.
minus 1, t1, this thing, and this is t2, t2 cube. So to represent, so here I need to go up to degree 2 to represent things that are, okay, I'm considering the unit interval, 0, 1, and so 0, 1 is here given by t1 minus t1 square, and here by t2 minus t2 square. So I need to represent functions that are non-negative on this unit interval in terms of sum of square in t1 plus another sum of square times this. And here I only need to consider summands up to degree 2. And so I have the monomials 1, t1 square. Whereas here I need to, how is it?
Yeah, how the second?
Here I need to go up to degree 4. 1, 2, 2 square, t2 3, t2 4. So this gives me a subspace of this direct product polynomial rings, which is down here, unfortunately. And well, the one here is not the one in the ring, but I mean I have a 1, 0 and a 0, 1 idempotence. The sum of the two is 1. So this I wrote up the linear subspace of this direct product with these basis vectors. Then how is it? X1 is, so if I write E1 is 1, 0, E2 is 0, 1, the idempotence. Then X1 is minus E1 plus T2. X2 is T1 plus T2 cube, and so I consider E1, T1 square, E2, T2 powers up to T2 4. 8 or 9, 8 were probably basis vectors, and so E1 plus E2 is 1 in the ring. So my linear functionals should be normalized, should have value 1 on 1, so this gives a condition relating these two. And then I'm expressing x1 and x2 using these identities, and there is 5 additional variables left over, which I called y1 to y5. And
So you have
at least in principle, I think it should.
Ring, right? You have idempotence in this ring,
Yeah.
and then you represent them. Well, okay, idempotence must be positive, semi-definite. Is it?
Well, I mean,
what
all this represents linear functionals not on the entire ring, but on a finite dimensional subspace of the ring.
Okay, yes.
right? I mean, we are dualizing kind of generalized measures.
But what Dima wanted to say, I think these functionals are represented by measures supported by the purple lines.
Yes.
By the vertical segment.
Horribly. I mean, this is kind of
So
asking a
so
truncated
if
moment
the
problems. I mean,
Singular
Yeah.
measures.
yeah, yeah,
Well,
Yeah.
on each line, different measures.
yes,
and then
exactly,
the combinations.
exactly, yeah,
That's exactly
Yeah.
the concept.
exactly.
So if the third S is defined by concave polynomials, then is this true in the conclusion true?
If S is defined by
concave polynomial. So it's G1 and like Tm is none. And each Gr is concave. But not strictly concave.
you are the specialist in this.
Well, I thought that. Why you the strict? I assume the strict.
No idea. I haven't. I nowhere used anything like convexity or concavity or anything of these defining functions. Like you did successfully. Okay, we switch it off.
Yeah? So, I think it's time to go. Thank you very much.